supported on beams, ductility, seismic reduction factors, and over the strength of confined masonry structures, modelings of masonry structures and earthquake-resistant structures. His accolades and work have a long list, and it is our utmost pleasure to have Dr. Juan join us in this series of lectures today. Sir, I know that it's like 11:30 in Mexico, and we are very grateful for you to join us at this time. And for all the participants, I'd like to let you know that he'll be delivering a session on experimental experience of confined masonry. Over to you, sir.
Thank you. Thank you very much. First of all, thank you for the kind invitation. I'm very happy to be remotely in India. I've been already a couple of times in Ahmedabad, so it has been a pleasure to be there, and I'm very pleased to have the opportunity to share with you some of the experimental experiences that we had in Mexico. So I will talk a little about that. I will try to share my screen if that is okay.
It's already shared, sir.
Okay. So I will, this is the contents of my talk. First of all, I will try to show you some specifics of the system of confined masonry that is used in Mexico. I will show you some structures and how we understand confined masonry in Mexico, first of all. Then I will show you very briefly a general model referring to the model we basically use for shear forces. That is a main thing in confined masonry. I will show this model just to have context that we will use in all the talk, and then I will just say a few words about some general notes about this why we do experiments and what is the intention. It's not always as clear as one would expect these things. So I will make some notes about it. And then I will go through some of the experimental campaigns that we have developed in Mexico. I will start with the effect of aspect ratio and show you the experience we did and the conclusions. Basically, in all the cases, I will basically present the problem, show the experimental program, and show some of the conclusions that we arrived with the experiments. Then we go to shear moment interaction. This was a very interesting, I think, very interesting experimental work. And then we will go to joint reinforcement contribution. We have a few tests for pseudostatic tests and also some shaking table tests. I will address both of them. And I will show you then some work on walls that are supported on beams. And the flexibility of the beams changes the behavior of the walls, and some design need to be done regarding the beams to be sure that the walls won't suffer some damages. And finally, I will present some infill walls. In this last experimental work, we try to understand the contribution of the confinement and also joint reinforcement in this type of walls. So if I may, I will start with this. These are some structures of confined masonry in Mexico. I am presenting these structures mainly because masonry is visible. Not always the masonry is shown like this in these buildings, but these are, as we call masonry, this that is special to be shown. I mean, to be apparent. And this is let me probably I skipped one now. Okay, this for example, this example is showing while construction one building, and I wanted to show here in this slide that we very much use a combination of masonry and concrete walls. Here is clearly shown. Normally, because these structures are in Mexico City, that we have very high seismic excitations, and normally the masonry is not enough to resist those forces. So we need to add some concrete walls to provide enough strength. And so this type of combination is very much used in Mexico. Also, is typical in the structures in Mexico. I think this is also the case in India. We need a parking space, and this means that in many cases, masonry walls don't go down to the I mean, to the ground, and are supported on beams or on other concrete walls. This is an important thing because we need to address the problem of supporting these structural walls on beams, for example. And this is something that we have studied and provided some guidelines for design. And I always start with this figure because give us what we think, what we understand with confined masonry in Mexico specifically. And these are the specifications for the confined masonry in Mexico. Basically, we have masonry panels that are surrounded by reinforced concrete elements, beams and columns that we usually call tie columns and tie beams. And here in the figure is specified the spacing of these elements. The tie columns should be placed whenever two walls meet or in corners. There should be always a tie column. And tie beams are the horizontal elements, and also it should be provided, usually, in particular in Mexico, these tie beams coincide with the level of the floor. But it's not always the case because sometimes the walls are too tall, and so the windows don't go as far as to the roof. So sometimes we need some reinforcement around the windows, and then we need a top tie beam that coincides with the floor, with the slab. Like here is shown the slab. This is important because the slab connects to these tie beams, and this connection is very important because inertial forces, seismic forces, are transmitted by the slab to these elements, and to these elements then to the walls. So this connection is very important. Usually, all the design of structures is based on the assumption that the slab is a rigid element that couples the movement of all the walls. That is a basic assumption. And so this is the basic framework. The construction process of confined masonry, probably you have seen this previously, but the panels are constructed first, and then the tie columns and tie beams are cast in place. This is a very important aspect of this type of construction, because it guarantees this a connection between the concrete elements and the masonry panels. And this is the shear displacement general model. I just wanted to refer to this curve because defines it represents a shear force, a lateral force in a wall, and the corresponding displacement at different steps of the loading. And we identified three important points. The first one is this one is called the slope of the curve changes, and it means that some cracking have occurred. And this is the first major cracking due to shear, and is a very important point. When the wall starts to get damaged and first cracking appears, then usually the wall can take more lateral load, and eventually reaches this point, which is the maximum or is the strength of the wall, is the maximum lateral force that the wall can resist. And from there, the strength start to degrade, and goes this curve. The displacements continually increased, but the force we need to apply to the wall start to decrease. So the strength of the wall is getting down, and usually failure is considered when this force get to 80% of the maximum value. But this is just a consideration. I mean, there's no theoretical things about it. Just the value that is most publications show this value as failure, is the failure of the wall. So this is the general model, and the corresponding displacements. This is the displacement at the cracking, the first cracking, and displacement at the maximum strength, and the ultimate, or the displacements at failure. And during the talk, we will refer to this cracking point or maximum strength, and we will now can understand what we were talking about. I want to make these few notes about experimental work. When we do experiments, we usually, I mean, there are two ways to understand or to pursue an experiment. In the first case, I'm showing here that we have already an hypothesis. But this hypothesis is something that we want to see if it is true. And so we do some experiments to try to verify that if this hypothesis is true. The interesting thing about this procedure, and it's called a priori hypothesis, is that we already have a model of, for example, for walls, and we have some explanation that we need to verify if our explanation to some phenomena is correct. But we have developed this this idea or this hypothesis based not on the experiments. We have developed this hypothesis based on probably theoretical thinking or other means, but not the experiments themselves. This is a very important way of doing experiments, because we already have developed the basic idea of how the experiments should work. And we are just trying to confirm if our hypothesis is correct. In the second case, interpretation a posteriori, then we made experiments. And the idea of this type of experiments is to find out is most of the time we have some idea of the basic variables that are important for our experiment. And but we don't know how these variables will actually modify or affect the behavior of our structure or wall or whatever we were testing. And just we want to see how these variables changes the behavior of our structure or wall or whatever. And this way of doing is not as strong as the previous one, because we will try to draw some conclusions from the experiment based on the experiment. So we can always produce some explanation if we have already the data. And this is, I mean, this way of doing is valid, I think, but is we need to be very careful of how our explanations are drawn from the data. Because remember that we can always draw some conclusions. If you have the data, you can always make an explanation. So we need to be very careful in that case. And there are other reasons why we do experiments. One important aspect is that we need data, for example, to validate or to calibrate design expressions. Say you have developed some expressions that predict, for example, the shear strength. Okay, you need experiments to have data to compare to and to validate your expressions. This is an important thing, that you need data to see the reality and confront it with your design provisions or design expressions. Other thing is you need data for numerical modeling. This is a very important thing, especially, for example, shaking table tests provide very valuable information for numerical modeling, because it's the only way that you have data, real data, that you can confront your models with reality. And if you are taking your research truly seriously, you need these models, but you need to be sure that they represent reality. And then you need this type of experiments to gather information data so that you can confront these models to reality. And one thing I want to stress is usually we don't do statistics with these experiments usually. I mean, when we are doing, usually we test a very limited number of specimens, and our objective is basically never is the objective to provide statistical significance with the information that we are gathering with experiments. The exception is when we gather many experiments and we try to do the statistics, but that's different. And these are review studies, and they are very valuable. But usually they have the problem that the data comes from very diverse environments, and so it's the variables of the problem usually have a lot of variance, and it is difficult to understand the problem in that way. But anyway, very interesting and valuable review studies have been published, and they serve a main thing that these type of studies are able to identify and detect meaningful parameters that are important for certain phenomena. But usually, because it's a statistical thing, doesn't come from an explanation for mechanics, for example. It's just, for example, regression models that try to identify what is the variation of one parameter and one variable of interest. For example, aspect ratio and strength of masonry walls. You can use a statistical model. In that case, you will have some kind of regression model, and you will find some coefficient. But I mean, it's something, it's useful. Japanese have made this type of experiments successfully, but they lack the understanding from the point of view of theory or mechanics, for example. That's why I think the explanations are most of the time, I will call them a bit poor, in the sense that there's no real understanding of what is going on. So I just wanted to share with you these ideas of how we use experiments, and I will show you some examples of one of these different types in the next examples. I will start with a study that we developed many years ago. That the idea was to identify what was the effect of aspect ratio of the masonry walls and the shear strength. The thing was that in the Mexican code, there was a shear strength formula that only depended on the area of the cross-section area of the wall, and all parameters such as the axial load, axial stress, and the shear strength of the masonry. But the aspect ratio of the wall didn't appear in those formulas. And in other countries for reinforced masonry, for example, in US, the aspect ratio already appeared in the formulas. And so we wanted to see in confined masonry what was the effect of this parameter in the shear strength of the walls. And so we conducted experiments, and we designed the experiment that, okay, let's apply lateral forces to walls with different aspect ratios, and let us see if there is a difference coming from the aspect ratio of the walls. And so we tested these 7 walls. Is a series of walls have the same height, and the length of the wall was varied. So the aspect ratio of the walls changed from very slender walls. The first one is have an H over L height over length ratio of 2.13, next 1.48, etc. And up to a very long wall that with very small aspect ratio. And for these experiments, we use type of masonry units that are very much used in Mexico. There are these machine-made clay units that are with multiple perforations, and are very common in Mexico. And so we here are some photographs of specimens being built. Here in the left part is the very slender one. The right one is a small slab that we construct in top of the walls. This slab is used for connection of a steel beam that serves to transfer the lateral force. We will see next. And here is in the left side is an example of one of the long walls. This is M6 one that has an intermediate tie column, and actually this is the very long one, and so I have two tie columns within the wall. So it's a very long one. This is obviously when we start to build the walls, we need to set aside some samples of the masonry, and these samples are used to be tested, and so that the material properties can be obtained from these samples. The idea is that the samples should be created or built exactly with the same material during the construction, exactly, so that they are representative of the actual masonry that is in the wall. So the same material that is being used for building the panels should be used for these samples of material. Here is an example of some details of how the bedding of the masonry is specified in Mexico. Actually, for this type of construction, the bedding should cover completely the face of the masonry unit. Here is not shown completely covered, because usually the mason covers it when he presents the unit that he's to put on top, and then make this coverage of the face of the masonry unit, and then puts the next one. In the right example, it is showing how this is done by the mason. Again, some samples in the right. Here are some of the walls already finished. They are usually painted in white because they are very easy to. It's easier to see the cracking in this color, and this once you identify the cracking, usually we mark them with a marker, and so that they are visible, and usually you put some note on when the cracks appear with a number. Usually, the number that you put aside of the cracks is the cycle number. Is because we usually applied a set of cycles with varying intensity of the lateral load, and so you have like you always have a cycle number that you can assign to the cracking. So you have an idea of the evolution of the cracking in the wall. Here's the setup of used for. There are two setups. The one for the shorter ones, the shorter walls. Observe that we have a top beam. This is a steel beam that is fastened to the wall with bolts, high-strength bolts. We have seen how these were built. This small slab where the steel beam is put on top and then fastened to it. And these are actuators. This is the lateral one and two vertical ones. This was a type of setup that we used many years ago. We don't use these vertical actuators anymore for this type of tests because we have seen that it's very easy to put some dead weight hanging in the wall so that you can apply the vertical load, because these two actuators are placed here to apply vertical load, and this one is to apply the lateral load. And the idea of fastening continuously, basically continuously, the steel beam to the slab is that to model the inertial forces. I mean, you applied the lateral load here, but you are transferring the lateral load more or less continuously to the wall through these bolts that are used to fasten the beam to the wall. So that is very important, because I have seen experiments by other authors that the load is directly applied to the left side of the wall, and then the behavior of the wall is quite different. So careful is needed for this. This is a second type of setup that was used for the very long walls. Observe that we have here 3 points where we applied vertical load, and actually we can see only one of the actuators here, but are 2 side by side, and that are controlled simultaneously to provide the load, because of the long walls required a very large forces to fail them. And these actuators were 50 tons, and 50 tons was not enough or was very close to the required load. So we actually used 2 actuators to be sure that we will have enough lateral force to apply to these walls. And again, this is a very long beam, completely fastened. And we use this auxiliary beam here just to be sure that we are spreading. I mean, this is a spread beam, that this concentration is spread as much as possible to the wall. I mean, obviously there are some concentrations, but basically the idea with the beam here, a very, strong steel beam, that the force is applied here in one point, but is spread to the wall. Obviously, it's never uniform, but anyway, that's why we apply it in 3 points to be as uniform as possible. This is one of the long walls. However, this one, it doesn't have an intermediate tie column. This is the longest one, is the M5 one. Is a very long wall without an intermediate tie column. Observe the long wall, the long beam. Here for this wall is only 2 points for vertical load and only one actuator. But here, this one is similar in length, a bit longer, but this one already have an intermediate tie column here in the middle. And for this case, we need two actuators. So this device has this kind of extra element here in the side of the wall and another one in the other side, so that simultaneously we are applying the lateral load to this wall. And this is the example of the setup we already showed in the diagram. These are the crack patterns. Usually, I think it's a good practice. We have usually, we ask one or two students to draw these cracking patterns, and are useful to keep it in the records of the experiment. And the photographs not always is the best way. These diagrams are very useful. One note is we can see some differences. For example, these walls don't have any horizontal reinforcement, so you can always see these diagonal cracks. Usually they open very much during the tests, and for longer walls, some horizontal parts start to show. So some sliding along this crack happen, but it's a combination of these diagonal cracks and horizontal cracks for longer walls. Here you can see that you have these two sections, long sections with horizontal sliding, and this combination with these diagonal cracks. These diagonal cracks are called are due to tension. Actually, they are called cracks due to diagonal tension, and so it's a combination of sliding and diagonal tension. All the other cracks are inclined cracks, meaning that they come from shear, but is a mechanism. Actually, the cracks are produced by tension in the perpendicular direction of the crack. So this is a typical way of cracking in masonry. This is the main result. These are the drift and the shear force applied, and this one, this value, these shear forces are normalized with this value Bn. This value Bn is the shear strength that the previous code in Mexico predicted. So we normalized with that shear strength, and you can see that for slender walls, that are these ones here at the bottom here, are not that bad. I mean, for the slender walls, particularly the square wall. For example, M4, no, M4 is already here. So for these ones, they appear to be reasonably okay, the prediction of the code. But when you start to have longer walls, the deviation is quite large. So the strength of the walls are much larger than the one predicted by the code. And so we developed an explanation, kind of theoretical explanation of this phenomena that is related to the different type of deformation of the walls. Slender walls have deformations basically due to flexure, and long walls have deformations basically due to shear. So because of this difference, we gave some kind of explanation of what we have seen in the experiments, and we ended up with this prediction formula. But the experiments show the red curve, and well, the explanation, but this mismatch was that our simple model didn't consider that the tie columns get closer, and so they provide additional confinement that we didn't consider in our simple model. So that's why we assumed that the difference was because of that difference in the distance of the tie columns. But anyway, the result is evident that that the formula that we were using in the previous code, the 2004 code, wasn't correct, in the sense that for long walls, the prediction was very small compared to the values that we have seen here. And so anyway, our prediction was kind of in the right direction. The good thing about the prediction was that when you create this prediction, I won't show it because it will take too much time to show. Is that it involves more parameters. For example, it involves the material properties, for example. And that is very important because you have then a sense of how the material properties are involved in this behavior of the walls. Another result of this of these experiments is this value of we call it K0, is the maximum shear capacity and the shear force at the onset of cracking, this one. So this ratio is important. And as we can see, this ratio is also dependent on aspect ratio. This is the aspect ratio. This is becoming longer walls. And one important is evident here is that very slender walls, the cracking point and the maximum point are basically the same. This is interesting behavior. And for example, for square walls, this is the basic aspect ratio. Most of the experiments with walls have been done with aspect ratio of 1. So this is a very important specimen. And we can see that we have a change in the, you can arrive at a much larger value of shear than the cracking point. And in the model that we just saw previously, is the way that we presented it in that curve. I mean, from the cracking point to the maximum shear, usually there is some distance. And clearly is shown here in the square wall. And for other walls, large, with small aspect ratios, this is also the case. Not as large as this one, but anyway, is evident that we have some extra capacity beyond the cracking point. In a study that some researchers did from many experimental studies, where nearly crack square walls were gathered information from. This average value that they found of this ratio was 1.3. So with this data, we will use in our formulas, we will see later, that we will use this ratio um, to predict the maximum shear capacity from the cracking capacity. So we just is a factor that we just said this K0 is 1.3 if for long walls, and is 1 just for slender walls. That is very simple, very basic. And with these results, we produced a factor to correct the 2004 formula for shear strength, and we applied a factor to correct for walls with aspect ratios less than 1. And the right part, we left it untouched. That was the decision. And I will show you what is the formula that we proposed. An important thing that is not seen from the previous, or probably can be seen actually, but anyway, here is presented more clearly, that after we arrived at the peak strength capacity of the walls, there is a difference in the strength degradation of the walls. The longer walls degrade very rapidly once they reach the maximum capacity, and they, with additional deformation of the wall or additional drift, rapidly they and in some cases abruptly fail. But this is not the case for slender walls. Observe that this is the degradation of the very slender one, the first specimen M1, and the rest start to degrade more rapidly. This is a characteristic that is interesting to behavior of the walls. This is finally the proposed formula. That after these simple experiments, and this part of the formula is the cracking prediction, and this factor is a correction factor, as I already mentioned. This correction factor is for slender walls. We leave it untouched. I mean, it's F1 is 1, and for long walls, this value varies from 1 to 1.5 up to this value of the aspect ratio. So intermediate values, you need to get intermediate values here from values, how we call it. Okay, I missed the word. Okay, so it's between 1 and 1.5, and this is the main parameters of the formula. Is the diagonal compression strength, this number, the wall cross section including the tie columns, this one, and this one is the axial force. So the result of the experiments is basically this factor, and is now in the code. This was a very simple, not so easy to do the experiments because of the long walls, and the setup was kind of difficult to carry it out correctly. But anyway, it was very nice and worked very well. Another example is this one, the shear moment interaction. This is one of my favorites actually, because it's one of those experiments where we already have the prediction. So we have, but first of all, the idea. The shear strength should be affected by the applied moment. That was the main idea. And but the shear strength code expressions in most cases don't include the flexural moment that is on top of the wall to predict the shear strength capacity of the wall. And we thought that this was odd because some very basic experiments conducted in Peru showed that this should affect the moment, should affect the shear capacity of the walls. This is the experiment. Observe, they produce a two-story wall, to say it that way, and they apply just a lateral load on top. And observe that the shear diagram of the shear force diagram is constant, and the moment obviously increases as we go down the base of the wall. If the moment is not producing any effect for the cracking or the shear capacity of the wall, then any failure could have happened in the first or the second story of the wall. But that is never the case. I mean, they always fail at the bottom. So this means that moment has an obvious effect on the behavior of the wall. However, although this is very evident, no formulas that I know include this effect, this interaction of moment and shear capacity. So we decided we produced a very simple hypothesis based on this idea. Okay, we said, okay, cracking should happen to some fixed lateral drift. And if we have a moment applied on top of the wall, then this moment also produces lateral displacement. And obviously the lateral force produces some lateral displacement. So we call this the displacement due to shear, and this displacement due to the moment. So if there is no moment, then the lateral displacement should go from here to here, or all provided by the lateral force. If not, if you have a moment, then the lateral force that you need to apply, so in order to crack the wall, need to be less. This is obvious. So this is a very simple idea. Well, I mean, using some very simple strength of mechanics formulas to predict these displacements, okay, with a moment and the lateral force, we end up with a formula that calculates this value, this cracking shear strength, divided by this value Bn, that is the cracking point when no flexural moment is applied. So we produce this ratio, and this is the formula. The formula is dependent on many things. W is the aspect ratio. Beta is a normalized moment, and eta is the ratio of the shear modulus and the elastic modulus. This is eta. So these are material properties. This is the aspect ratio, and this is the applied load moment. So this is a very, simple formula. Well, don't look that simple, but this is the plot, and so it shows that, and this is the normalized moment. So the reduction of the shear capacity using this normalized moment shows that for different aspect ratios, it shows you how much the shear capacity have reduced. And so it's and actually it's very interesting that, for example, because for long walls, the effect of the moment is negligible. I mean, and it's very clear because for long walls, the flexural deformation is very small because they are very rigid. Flexural rigidity of the walls is huge. So so the effect of the moment for long walls is very, very small. But as soon as you start to get slender walls, the effect of the moment increases. But it doesn't increase, it's asymptotic. It doesn't keep growing. So it's asymptotic. So this behavior is very interesting. It's kind of consistent, as we will show. Well, I show it in, I won't show it here because again, it will take some time to show. But anyway, here are the main parameters. Again, this is the material properties, the aspect ratio, and the normalized moment. And so the interesting thing is that we came up with this formula and this prediction before we did the experiments. And so now we designed the experiments to try to prove this. And what we did was to test 6 specimens. Here are the description. The first 2 are made from handmade clay units. Then the last 4 are from machine-made clay units. The length of the walls, these were aspect ratio of 1. And the last 2 are more slender walls. And this is an important thing. I mean, the first wall in this pair doesn't have any moment, and the second has this normalized moment. And in the second pair, again, in the first wall of the pair doesn't have any moment, and a very large moment, and a very large moment. This is not normalized moment, but anyway, it was a very large moment. And in the third case, we applied moment to both walls, but different values. and so we predicted the reduction of the shear strength of all this. This is the setup. The setup is kind of complicated. In this case, the vertical actuators not only applied vertical force. Observe that in the back of this, there is also another actuator here. This one is also applying vertical load, but I mean, by making different values of the force in these 2 actuators, then we can apply a moment. So these 2 serve to apply a vertical load in conjunction with this one and a moment. And with this horizontal one, we applied the lateral load. The sequence of loading was kind of difficult. Here's, I mean, very rapidly because time is marching. We applied a lateral load, and at the same time we applied some moment. Here are some up to. Then we decided to, when we arrived to a certain lateral deformation, we stopped applying moment, increasing the moment, and continue applying shear, so that we arrive to the cracking point. And that's how we applied. We know exactly the moment that we had applied, and see what was the cracking force. That way was the experiment was designed. These are our results. In the green ones, the green lines show the envelopes of the wall that had no moment applied on top of the wall. And the blue one is the one with moment. And these are the cracking points. And these are the values that we found. Here one is with very large moment applied, this blue one, and this with no moment. Again, the cracking points are shown here. And this one, both have moments, and these are the cracking points. So clearly, the moment had an important effect. And these are the predictions. So here are the values. This is the cracking and the nominal, the one that was and the one with no moment. This is BN, yeah, because I have no moment. So is the usual one, and this one is less, and the cracking was presented for a smaller lateral force, and the ratio is 0.692. This was as calculated, and experimentally we found 0.77. It's a 10% error. And for the second pair, similarly, this was 0.4 was the experiment, and 0.358 the one calculated. This one calculated with the material properties and so on. And again, around 10% error. And the last ones, we need to get the quotient of these two and then calculate it, and then the quotient of the experimental ones. And here the error is just 0.5%. So, I mean, we concluded that the prediction formulas were very good, and observed that in this case, we cannot cheat in some sense, I mean, to say some words, because the predictions were already there. We didn't make the predictions with the data of the experiments. You can always make the numbers coincide with the experimental ones, but in the reverse way, it's not possible, because you already come with the prediction. So that's why this experiment is very strong in the conclusions that you can draw from them. Okay, this again the normalized moment. The question is here. We ask what is the actual value of this normalized moment in actual structures? That was the question, and this is not experimental. Well, this is numerical experiments. We found. I mean, we asked some engineers that had a structural engineering firm, and asked them to share with us some of the masonry buildings that they have analyzed. And with this information, we analyzed each of the walls of their analysis, and so we can calculate the moment on top of the wall and make the actual normalization. And we found this. Each point is a wall on one of those structures that I just showed you. And this is the moment, the normalized moment on each of the walls. And so we can see that beta can be negative. When beta is less than 0, it means that the wall is bending in double curvature. And so the effect of moment is not, if anything, it will increase the shear strength, but not reduce the shear strength. But anyway, these points are not important in this investigation because the effect of moment is not reducing the shear capacity. But all points with beta greater than 0, all these points have a reduced shear strength. But observe the aspect ratios, because for very long walls, I mean, even if you have large moments, the effect of the moment is very small. The important effect is around these points and these ones, because they are more or less slender, I mean, nearly squared walls, but have large normalized moments. And if you see the predictions, this blue line is here here, the aspect ratio. And for these normalized moments, you can find reductions of, for example, 25% if you have a beta of 1. Beta of 1, yeah, we have some points here. There are few. So this is good news, because it means that the shear moment interaction is important for few points, for few walls. Those walls that have some more or less slender walls and have large normalized moments. There are few. There are few in, I mean, in all the structures that we analyzed, are very few. But there are very few ones that are very slender and have large moments. These are dangerous ones, because they could fail easily, because the shear capacity is reduced enormously. I mean, it can be as less as, I mean, 40% reduction of the shear capacity. So this is the formula we came up with to predict the shear strength at the onset of cracking. We already applied the SF to include the aspect ratio, and this term is the reduction of provided by the applied moment, that is MA, on top of the wall. HK is this value, is this modulus of elasticity, the inertia of the wall. This is the lateral stiffness of the wall and the height of the wall. So a very simple term, but predicts the thing that we just showed you. So it was a very, I have to say that the experiments very, very hard to do. Were very difficult to do, because we need to synchronize all the actuators perfectly, and it was kind of nightmare, the experiments, but we were very, very happy with the result. Let me show you how much time I have. May someone tell me how much time I have? Okay. Okay. I think we have still a few minutes. Yeah. Let's go for this this case. We studied the effect of joint reinforcement in the behavior of confined masonry walls. Actually, I should say that confined masonry is used with reinforcement in Mexico, but it's not very much used in any other place in the world. Although we have studied a lot, in particular lately, we have studied this this effect, and other researchers also in Mexico have proved that it's very beneficial. Let me show you the idea. So the basic hypothesis is this diagram. I mean, you have a basic cracking pattern of 45 degrees, and you have forces that are developed in in the joint reinforcement. Here, joint reinforcement is shown with red lines, horizontal lines, and in some and the effects of this reinforcement are known already when we started these experiments. That they reduce the crack width, that they reduce the strength degradation rate is a very important thing, that the walls are more stable, that act like an additional confinement so that they improve the displacement capacity of the walls and increase the shear strength. These are the effects of the reinforcement. And the contribution of the reinforcement was in the previous Mexican Code of 2004, that this was the formula. This is the percent of a steel area of the reinforcement. This is the yielding stress, and this is the area of the wall, including the tie columns. And this eta is it was, because this formula is not used anymore. This eta was an efficiency factor that was defined as 0.2 for this amount of reinforcement. This was in megapascals, and or 0.6 if this value was less than 6. So this was a very simple formula. Actually, this is the same formula used for many codes, and this value of eta is between 0.5 and 0.8 typically. And this is the simple formula. And but I should say something, that this simple formula produced inconsistent results. When we studied this phenomenon, we found that because these formulas are not dependent on the compressive capacity of the masonry, it happens that walls with very bad masonry, with very small compressive capacity of the masonry, can reach very large strength predicted by this formula because of the reinforcement. So it was a strange idea that a very poor masonry, in the sense that they have a very small compressive capacity, can increase its shear strength because of the reinforcement, and very significantly. And so the effect was very negative in the profession, because usually, I mean, the engineers didn't want to put good masonry, because with very bad one, a very cheap one, they can produce very nice strengths. And so there was no need for a good masonry. And that was very unfortunate. And so we tried to figure out and try to do very precise experiments to show what was going on. And the idea was very simple. We just produced many walls, say 6 walls, with different amounts of reinforcements. So the first one didn't have any, and then increasing values of reinforcement. And the spacing of the reinforcement was constant in all the walls, and so in some cases there was a lot of reinforcement in each layer of reinforcement. Here are the bars that we used. Very simple. The units were multi-perforated concrete walls, or concrete units. We did very similar experiments with different units. This was machine-made clay multi-perforated units, and very similar amounts of reinforcements. So a total of 12 walls were tested. This is the setup. The setup is kind of different than the ones I have shown you. because as I mentioned, this is a very practical, very useful way of applying the vertical load, because it's maintained constant, perfectly constant during the experiment. And so we, after the few first experiments that we did many years ago, we are using this setup for applying the vertical load. It's very convenient. And here, the normal thing, I mean, this steel beam well fastened to the wall. And this is the reinforcement. We included strain gauges along all these wires. It was a hard work to do, and also costly, because each strain gauge, I don't know, is costly. But anyway, the idea was that we have enough information that with the deformation we can produce the stress in the reinforcement, and eventually the force develop in each wire. And with the force in each wire, then we can produce the contribution of the reinforcement to the lateral reinforcement. I just want to stress one thing, is that we need to remember that the reinforcement actually doesn't resist any force, because you can see easily that the reinforcement is not anchored anywhere. So it's flying, is in the air, is not anchored to any support, so cannot resist directly forces, lateral forces. So the actual mechanism for the contribution of the reinforcement is that they provide the means for the cracks to be closed, and then the forces can be, can be transferred from one side of the wall to the other, and then cracking appears in other parts of the wall. And so the transmission of the forces through the masonry is more efficient. And but in the end, the only element that resists the forces, because it's supported in the base, is the masonry. So the masonry is responsible for any resistance of the wall. But anyway, we have in our minds, we said we provide horizontal reinforcement, and we attribute some contribution of the reinforcement as if it were directly participating in the resistance of the forces. This is not the case. Only the masonry is providing resistance. And this is a concept very important, because it's not possible that a formula that gives the contribution of the reinforcement, that it does not include the strength of the masonry. Is absurd. And so that was our main idea when we started the experiments. And so, this is the type of loading, cyclic loading. This is standard. And these are some of the cracking patterns. This one is without reinforcement, the first one, MB0. Observe that usually only a few cracks, diagonal cracks, that open very widely. And as you start to include more and more reinforcement, more cracks appear that are less wide and more distributed all around the wall. And actually, in the end, they damage more as for example, compare this MB0 to this MB5. MB5 has a lot more reinforcement, and actually, in the end, the wall gets more damage in the end at failure. This is because, as I was saying, because the wall gets damaged everywhere, and so I said, one way to say it is, we take all the juice of the wall, to say something, and we extract all possible capacity of strength of the wall, of the masonry. And these ones are the clay ones, similar thing. I want to show you this set of photographs of the experiment of the wall without reinforcement. Let me show you. It's a small one. So we are start applying lateral forces, and this is the first cracking. Yes, diagonal cracks. This is where the slope of the curve changes. Observe that not many new cracks appear, just the first ones start to grow in its width, and now the crack has penetrated the die column here in the bottom, and is close to fail. Now the wall failed because of this crack penetrates the die column. This is the end. Let me show you this one. This one is similar but has this amount of reinforcement. It's mid-table wall. And again, some diagonal cracks will appear. These ones are actually, these ones, small ones here at the bottom, are flexural. Are flexural. The main cracking, the first shear cracks here are these diagonal ones. Observe the distribution of the cracks. Because of the reinforcement, the forces can be transmitted from other parts of the wall, and so other parts of the wall also get damaged. But see, the opening of the cracks is much smaller. The width of the opening is much smaller. But in the end, the wall gets more damaged. Okay. So this is the difference between having or not having reinforcement. This is the main finding. The main finding is that this is the contribution of the reinforcement to the lateral force. This one obviously MB0, because have no reinforcement, has no contribution of the reinforcement. Then we included some amount of reinforcement increase. I mean, this is the contribution of the reinforcement, and this is the force. And this is MB2 and MB3. But then came MB4 that has more reinforcement than MB3, and MB5 more than the MB4, and substantially more. And suddenly the wall doesn't increase its strength anymore. And once we arrive nearly MB3, although we included more reinforcement, the wall does not resist any more shear force. So what happened is that the shear capacity of the wall has exhausted. And this is a critical point. And this is the amount, the maximum, well, not the maximum, we call it the limit reinforcement. After this limit reinforcement, if you add more reinforcement, you won't increase the shear capacity of the wall. So this is a critical point. And so based on this limit, we have included a maximum value. So we can include more reinforcement than this one, even though we cannot increase the shear capacity. It has been shown that the displacement capacity is increased. So it is is still increased with the amount of reinforcement. So we decided to include a maximum amount of reinforcement larger than this amount of limit value. And the limit value can be calculated, and this is the important thing, can be calculated in terms of the masonry compressive strength. And this value is the net area of the units, the masonry units. And lambda is a constant that is dependent on the experiments. And is 0.1 for the experiments that we did. And so observe that this maximum amount of reinforcement, or not maximum, again, the limit amount of reinforcement that marks this point depends on the quality of the masonry. That is a main contribution, I think, of this study. We also calculated the shear capacity due to the masonry and included some other studies did in the past. And we found that the contribution of the masonry consistently reduces with amount of reinforcement. So if you add more reinforcement, the masonry actually gets more damaged, and the contribution to the lateral strength can be thought to be less. But as I just mentioned, the only responsible for the response of the shear capacity of the wall is the masonry. This reduction takes account that we are including the other component, the component of the contribution of the reinforcement. Actually, that one increased, but the sum of these two numbers is the real capacity that always is of the masonry. This is kind of misleading sometimes to use these two components, like the one of the reinforcement and the one of the masonry. Actually, there is just one. The masonry is responsible for the shear capacity, but the reinforcement acts like some confinement that limits the opening of the cracks, and then the transmission of the forces can take place, and that's the contribution of the reinforcement. Anyway, so the formulas got more complicated, not that much, but basically we have the shear strength of wall with reinforcement includes the cracking strength. This K0 we have seen that produce the cracking and then the maximum, and this K1 reduces the shear strength due to the amount of reinforcement. And this is the contribution of the reinforcement. The contribution of the reinforcement is just like the previous formula. But this one is the effective amount of reinforcement. The effective amount of reinforcement is if the amount of reinforcement is less than the limit, then you can use as effective the amount of reinforcement included in the wall. But if the amount of reinforcement is greater than the limit amount of reinforcement, then you should use the limit. Because as we have seen, if you put more than the limit, then you cannot increase the shear capacity of the wall. So you take this limit. So the effective amount of reinforcement is. So you need to figure out that you can include some amount of reinforcement, but only part of it is effective for the contribution to the shear strength. Okay, so this was very important investigation because these formulas showed that are more consistent in the sense that if you have a wall that have a very bad masonry, then the contribution on the reinforcement is very small. And so if you want to increase the shear capacity, you need to increase the compressive strength of the masonry, and then the reinforcement can be more efficient. If not, then this value, because it's limited by the compressive strength of the masonry, could be very small. Wow. Okay. Let me see my time. I think I have 15 minutes still.
Yes, sir. Yes, sir.
Okay, perfect, perfect. Okay, let me show you. We also try to figure out the effect of the reinforcement in a shaking table specimens. So we conducted these experiments. We did two of these structures that is just an axis of a typical masonry structure, and we are testing this axis, and the direction of the shaking is in the direction of these walls. The structure is scale 1 to 2 because the shaking table of our lab is kind of small, not that small because it's 4 meters by 4 meters. It's okay, it's a good shaking table. But anyway, we cannot include a real scale structure like this one in our lab. So we scale it one to half. And this is a type of units that we used. These are multi-perforate concrete units. And the scaling, we scale the units by sewing this unit. Obviously, we didn't obtain a unit exactly scaled with all these perforations here, but actually we were able to produce a scaled unit that has exactly the same net area than this unit. So I think the scaling was very good, and was very difficult to achieve because each of these units had to be coated, sewn many times, 6 times, and so we obtained only one unit by each one of these normal scale units. So it was a very hard job, but anyway, we were pleased with the scaling of the units. We performed some elastic analysis of a model because we wanted to know with some precision what was the average vertical stress in the walls, because it contributes to the shear strength of the system, and because we needed to calculate the period of the structure so that we can determine the asymptotic accelerogram. I will show you that. And because of the scaling, we need to include more axial stress in the walls in order to represent more precisely the axial stress in a prototype. This is a common thing that happens when the scaling is done, that you need to add directly some axial stress, because you cannot add more load, because the load that was included in the here with some weights in the slabs, you cannot include more to add axial stress, because this load is included also in the as mass in the model, and so you don't want that. You don't want to include more mass. So you need to balance. I mean, the amount of mass and the shear and the axial stress in the wall. So some axial stress need to be provided separately from the mass. These are some difficult details for these experiments because of the scaling, basically. This is synthetic accelerogram. This is a very well-known technique that we produce a signal that have this target spectrum. The target spectrum is the target response spectrum of the structure is the blue one, and the actual one of this signal is the orange one. And the benefit of using this is that we can provide a signal that we are sure that will excite the structure, and we can fail the structure because of this. So we center this this upper part of the spectrum with a period of the structure, and so are very sure that after some cracking, this period will move to the right and still have large acceleration, so we can fail the model. And so this was very efficient and was performed very well, actually. We applied several movements to the specimen with the same signal, but we scaled the signal, the accelerations of the signal. So we increasingly the intensity of the signal was increased. Let me show you this this test. This model is without reinforcement. So, as you can see, the typical diagonal cracking showed up. The rest of the structure was kept basically elastic. No damage whatsoever was shown. These are the first story hysteretic curves and the envelope, and this is the roof deformation. And I mean, the deformation limits are based on the first floor or first story deformation. So checking, and one important thing is that in our code, we consider that the maximum deformation that is admissible in a structure is the one that corresponds to the peak strength. Because after peak strength, the degradation could be quite fast. And so it's not safe to include larger deformations than this one. And so this is the standard we used. This is the maximum allowable deformation. And this is the value. And these are some crack patterns. You see, it's exactly the typical ones we have already seen. Here's the cracking penetrates the tie column, and very few cracks actually, but very wide ones. This is typical of a wall with no reinforcement. Let me show you the the model with joint reinforcement. Here is interesting that you can observe this diagonal cracking, but the main failure mechanism is by sliding. So the thing is that again, this is the envelope and the hysteretic cast, and actually this moved. Oh, sorry. Okay, this line. Sorry, I moved this. Sorry, this line should be here. Sorry for that, because when I scaled the figure, I missed that line. Sorry, but this line was at this peak value. Okay, I will show you the results. The main thing is that the failure mechanism was sliding, and an important thing is that when the failure is by sliding, we need to understand that for the reinforcement to actually be activated, need to be crossed by the cracks. And if the main failure mechanism is sliding, then the joint reinforcement is not activated. And so, as we will see, because of this type of failure, then the specimen did not increase its strength. Let me show you. I will come back to this. Okay. The deformations, the deformations, the story drifts, the one without reinforcement was this one, and with reinforcement was this one. So actually it was a very nice increase. The Mexican code for this type of structure without reinforcement is allowed 0.205. So it is okay. This is the value we found. It seems that is in order with the code. This one is smaller than the one that the code allows. It's 1%. This is less than 1%. So probably the value of the code is a bit too large. And we did these experiments to check these values actually. And so this is very valuable information for decision making. If we will reduce the allowable drifts is a question that will be decided in the committee of the code. And this is what I wanted to show you, the strength. The strength of the system without reinforcement and with reinforcement was very much the same. This is due to the type of failure, because we have done other tests with other type of units, very similar ones, that was an actual very nice increase in strength. So we need to look to this type of failure mechanism in sliding more carefully, because we haven't seen this type of failure in pseudostatic tests, and basically not in actual scale specimens. And we think that this sliding was probably due in some way because of the scaling, but we need to investigate this, because it's very important that that if sliding is a likely failure mode, then the strength provided by the reinforcement will be reduced very significantly. So this is a very important finding, and we need to look more to this result. Uh, I will go through this one very, very rapidly because our time is nearly over. And I showed you your structures that are the structural walls are supported on beams, and this is a difficult thing for the wall because the deformation of the beams may damage the wall, and so we need to kind of design the beams so to be sure that the walls won't be damaged. And the behavior of the wall on top of a flexible element is like this one. You have stress concentrations at the ends of the wall. And these concentrations depend on the flexibility of the beam. If the beam is very flexible, then the concentration is much greater. If the beam is very stiff, then it tends to be more uniform. This load on top of the wall comes from other stories of the structure. There can also be some loads directly on the beam. This is this value. And what we studied is this concentration be such, this is the concentration factor that multiplies this average stress and produce the maximum stress in one of the ends of the wall. So that's why we call this FCE a concentration shear stress concentration factor. This is a unit for stress, and that leads to the maximum stress in the wall. And we need to check that this maximum stress does not exceed the maximum compressive capacity of the masonry. This is the main objective. So we need to kind of predict this concentration factor based on the flexibility of the beam. That's the main thing to do. And the flexibility of the beam or the relative stiffness of the wall and the beam is characterized by this parameter. Is the K parameter. It depends on the material properties, dimensions of the beam, and the properties of the wall. And okay, the problem also is that elastic models of wall supported on beams lead to inappropriate beam designs because basically when you do an elastic model with finite elements or whatever, and you add the beam, you will see that beams appear to be nearly unnecessary because, of course, the wall is a very large element that will take all the load. And it seems that the beam is not required. And these have led to wrong designs in practice, and we need to address this carefully. To address this problem correctly, you need to go non-linear, because linear models usually show like this. Stress concentration at the beam ends, okay, we have shown this, and the minimum beam depth is required to prevent deflection that will damage the wall. So controlling the beam depth controls the stiffness of the beam, and that will, as I show you, if the beam is very stiff, then this concentration is smaller and tend to be uniform. This contact stress between the wall and the beam. But if this is very flexible, then the concentrations are very large. So we need to design the depth of the beam so that this concentration, stress concentration, do not exceed the maximum compressive capacity of of the masonry. And so how to do it? I mean, We need recommendations for a minimum beam depth. Okay. And the methodology was to generate a reliable numerical model to conduct a parametric study. And for that, for that purpose, we conduct an experimental program of walls supported on beams to have data to validate the numerical models. As I just said at the beginning of our talk, this is a very important objective of an experimental investigation. For a nonlinear model, a careful characterization of the material properties is required. This characterization was addressed in the experimental investigation. This was a very difficult part of the investigation. These are the types of specimens that we have. One that are supported normally, and the others supported on beams. Simple supported on beams. These are the construction of the walls, just typical. Look at this constructed on the beam. And this was the first experiment that was normally supported. And there were two types of loads. Lateral load, but because we wanted to see if walls supported on beams reduce its shear strength. And the other was application of vertical load to see at what deformation we have damage in the walls. And as I said, basically to have enough data, so that we can compare the numerical models with the experimental results. Here are some material characterization. It's a complex task for nonlinear models. There are some very specific, more difficult parameters to know from the material. So this type of specimens with inclined joints were needed to be tested, and from this we found some shear capacity of the joints for large axial forces. These are pure shear forces at the joints of the masonry. So the behavior of the joint can be characterized. There are some other results. We included strain gauges on the face of the wall and some lateral instruments to measure lateral displacements and so on. The main parameter was this one, the vertical displacement at the center of the wall. This is the setup. Is standard one, basically. In some cases, we applied also lateral load, and in other cases, only vertical. This is one case with vertical. This is, okay. This was lateral, sorry. This is lateral. And this one, the orange one is the one supported standard normally, and this M2 is the one supported on the beam. So we found a reduction of the shear capacity of the wall due to the flexibility of the beam. And these are axial components. This is the displacement at the center of the beam, and this is the axial stress. And these are the different specimens. The blue one, this one, this is the actually is the remaining axial capacity of the wall, because this wall have been tested first with lateral forces and failed by lateral forces. So this value is very interesting because it's the residual axial capacity of the wall after being failed by shear component. And this can be thought as, if you see a wall that has been damaged by an earthquake, you can always ask yourself, if this wall is stable, meaning is capable of resisting the vertical loads, and usually, as we can see, they have a lot of action capacity left after being failed by shear. This is the modeling with all the information that we gathered from the materials and experiments. We check the experiments and the numerical models, and the comparison was very good. Also for the actual case. And then we perform a parametric study with varying the position of the wall on the beam, the position, and also the length of the wall compared to the length of the beam. Those were the parameters, the length and the position. And we end up with these curves that are the stress concentration factor, observed that are very large, and K is this parameter that represents the flexibility. If this value is large, then it's very flexible. The beam is very flexible compared to the wall. And so the stress concentration factor is very large. Normally, the walls, the beams are between 3 and 6. I think these are too large values. It would be a very, very small beam. These values of larger than 6. So, I mean, our elements, true elements in reality, we are between 3 and 6. And I mean, to have you some idea of these parameters. And so we ended with some very simple conservative formulas of stress concentration based on this parameter K. And so we can calculate the maximum stress in the wall and compare this with the compressive strength of the masonry. If this one is larger than this one, we need to increase the depth of the beam, and this changes the value of K. And with the value of K reduced, because if we increase the depth, this is reduced. Look, the inertia of the beam is in the denominator. So the K is reduced, and then the stress concentration is reduced, and then we test again. That's the design procedure. But basically, you end up with the appropriate depth of the supporting beam. And there is an additional recommendation that limits also the depth of the wall. The idea is to limit the displacement at the center of the beam to guarantee that the beam is not damaged. So one recommendation is to review that the stress capacity of the wall is not exceeded, and the second is the displacement at the center of the beam. And this is the shear strength reduction with also with the flexibility of the beam. We found that yes, there is a reduction of the shear capacity because of the flexibility of the beam. As we said, the beams, this K value is between 3 and 6, so the reductions are not too large, usually will be around probably 20% or less. So more or less is the type of reduction that we will find on the lateral strength of the walls. So I have some other things, but I think we can stop here. And I hope have been interesting in some sense, and thank you very much.
Thank you very much, sir. It was a really excellent lecture, and I think you have shared the experience of uh, testing and experimental facility which is available at your university. I
Yeah,
think we
well,
have.
part of
Yes, sir.
the not only in the university, we have a disaster prevention lab. Is an organization for disaster prevention in Mexico. It's actually very near the university, and it's a very good lab actually.
Right, right, sir. But it is really wonderful, and I think the way in which you have delivered this session is really wonderful. Um, right now it is 1:30 uh, in Mexico, and
Yes.
you have yeah, and you have delivered this lecture with so much dedication, sir. It is really wonderful. I think we approached you 1 week back, and you accepted our invitation immediately, and for that we are very much thankful to you, sir. And I think we all have enjoyed this session. Really wonderful.
Oh,
And
thank you.
uh, yeah, sir, we have also some facilities of testing facility at our institute also, and
Ah, very nice.
yes, sir. And we are focusing on the testing as far as the earthquake engineering is concerned. So we have a lab which is having shake tables and models, and we want to develop it further. So I think we will approach you uh, for to get the details how to go further as far as our laboratory facilities are concerned, sir. But sir, your lecture was really nice. Yeah.
Thank you very
uh,
much, and please do. If I can help in anything, I will be very pleased to do so.
yeah. Thank you, sir. Uh, now, participants are requested to ask questions. If
Yeah, of
Yeah,
course.
uh, uh, you can raise your hand or you can write in the chat box. Yes, Dr. Manish Shah, please.
Time kind of.
Yes, Professor Manish, you can continue. Unmute yourself.
I'm audible now, sir?
Yes, yes, you are audible.
Okay, okay, thank you, sir. Sir, my question is with reference to the experimental testing which has been done on large balls, that is large size balls. You had also shown the installation of number of strain gauges at different locations in the wall with reinforcement and without reinforcement. Uh, my question is that, sir, whenever there is a sliding, means whenever there is a sliding shear acting between the two bricks, which has been connected with mortar. So during that sliding, generally it happens that if the strength of the mortar is compatible with the strength of the brick, then in that case only there is a failure at the junction between the mortar and the brick. Otherwise, there may be a case where if the rigidness or the stiffness of the mortar is high, then it may protect the brick to have a shear failure. Means if the because internal particles of the bricks are not same at every junction, there may be some little bit variation taking place in the during the construction of the wall also. So, how did you analyze this, or how you differentiated that the failure is taking place not because of the rigidness of the bond or not because of the rigidness of the brick?
Okay. And well, we have seen this sliding failure. Uh, I show you a couple of times that we have seen this type of failure when the walls are are with aspect ratio small. I mean, they are long walls. When the walls are long, they this the sliding mechanisms tend to appear as part of the failure of the wall, and and we haven't associated this failure with capacity of the units, but of the capacity of the mortar. I mean, because I mean, if you see the experiments, you don't see that that there is the units are damaged because of the sliding, and so we haven't attributed the sliding to the units, but to the mortar and to the basically the configuration of the wall. And most of the time, we have seen a combination of diagonal cracks due to tension and this sliding. And but I don't know what to add to this. We haven't seen any evidence that the units get damaged because of the sliding. So we do not attribute the sliding to the properties of the units. I don't know if I answered the question because.
But sir, do you think that this process is really happening in the wall? Means I believe that this is the process that is happening in the wall, and it is due to the sliding shear only, because the sliding shear phenomena is quite different if I talk in terms of only brick, because the amount of the friction which is available with the brick surface and available with the mortar surface, there is a quite big difference between those. So definitely during that sliding shear, uh, the interface friction which is actually playing the role to achieve its maximum value will change as the wall is becoming more and more long.
Mhm. Sorry, probably I'm not understanding well your question. I'm not hearing very well, I think. Um, uh, uh,
Sir, if you permit, I can repeat my question.
yeah, uh, I don't really understand the main question. Is the question is regarding sliding? Why is sliding or?
Yes, sir,
Um,
sliding is taking place, but I am asking sliding with reference to the intermediate components of bricks. Means within the wall, when the bricks are sliding
uh-huh.
because of the tensile forces. Okay,
See?
so in
No,
that
no,
case,
no. Excuse me, because
yeah,
sliding, the tensile forces produce these diagonal cracks. We agree with that. Tensile forces tend to generate diagonal cracks.
okay,
Uh, the diagonal cracks are produced because of, uh, as we have called them, compression struts. I mean, there are fields of compression along the diagonal of the walls. And this compression produces tension in the perpendicular direction of the strut. And so these tensional forces crack the masonry. And usually the masonry is quite weak in tension. And so this is the mechanism by which the masonry is cracked in the diagonal direction. And sliding is a very different phenomena. Uh, Basically, it takes place because of friction, and the units are not very much affected by this mechanism. because the mechanism is always along the joints, and so the sliding is produced, but the units are not very much affected or contributed to the sliding mechanism. So these are two very different ways of damaging of the wall.
Okay. Thank you.
Sir, one question I want to ask that if we consider the the percentage of confined masonry construction in Mexico, what is the
Uh-huh.
percentage as compared to all other building typology? Confined
The
masonry?
the what do you mean, the dimensions?
No. Percentage uh, uh, of confined masonry buildings as compared
Ah,
to, yeah.
okay. Do you mean the amount, the percentage of masonry and concrete, or?
Yeah, percentage of
Okay.
confined masonry structures as compared to the concrete structures and other types of buildings.
Usually, I don't know the percentage. Let me think about it. Usually, in the first two stories, usually the engineers provide several walls in concrete to be able to resist the shear forces. And after that, then they continue the walls with masonry. And obviously, this depends on the zone of the seismic zone of the city. Talking about Mexico City, because there are many different parts of the city with different seismicity, and so for the parts of the city where is large, the accelerations, uh, you can have probably 30% of the walls of concrete. Uh, I mean, this is just I mean, I'm not an everyday designer of these structures as my colleagues do, but I usually talk to them, and we see these type of things in the committee of the code, and so we know that I know that the structures masonry usually have considerable amount of walls with of concrete. I don't know if 30, but I don't think more than 30% of the walls, but just in the first two stories. Uh, After that, you can continue with masonry. That is usually the case.
Okay, sir. Okay, sir. Yeah. Uh, we have some more questions from Ronak Motiani. Yeah, Professor Ronak, please. Yes,
Good
yes.
evening, sir, and I would like to thank you for delivering such a great lecture. And the experimental part was really very interesting to us. So
Thank you.
I have a small question. I need your suggestions on that. Actually, if you can throw some light. So you have presented the slenderness ratio considering from 2.13 to 0.48, and you have suggested some value of K, that is shear strength factor for different type. Now, sir, in Mexico, the Mexico earthquake, it is known for the soil amplification, and I read that soil amplification in Mexico earthquake was close to 5 in 1985. So, sir, if you can throw some light that how this slenderness ratio of 2.13 to 4 0.48 will vary with soil condition, like in soft soil or medium soil. Will this vary completely with soil condition, or what will be its effect with the variation in soil stiffness?
Mm, well, uh, let me try to understand. The I mean, soil always have a importance, and usually the masonry structures and many structures in the city are um, are supported on very stiff elements in the ground. This is customary. I mean, the general design methodology for supporting these masonry structures, because small differential settlements can have important impact in the whole structure, then should be minimized these differential settlements. And so very stiff foundations are always provided for these structures. So you're sure that the building, when moving, moves like a rigid body, at least in the foundation level. This is the general practice. And in regarding the amplification, this is related basically with the accelerations of the soil. I mean, so these are characterized by the spectrums that we need to use for the structures, and 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 obviously have a very large impact, as I was mentioning in another question. Because of these large accelerations, most of the time you need a lot of concrete walls and in the first stories of the building. This is a common way to solve the problem. And but more than that, I wouldn't. I mean, based on these parameters, you can design the building, and actually, it's very difficult to have buildings more than 6 stories high, and usually it's limited to that, because in the present version of the code, if you have taller than 6 stories,
Story.
you need to reduce the ductility of the structure by 0.5. So that means that you need to increase the forces, because ductility is used to reduce the spectrum. So if you reduce the ductility, you end up with larger forces, and so it becomes very difficult to to design a building with larger than six stories. This is typically the environment of the design of the building, no? And I'm not sure I answered your question, but I try to put the main things. I mean, the main components of the design and that we usually have to deal with.
Thank you, sir. Thank you. Thank you, sir.
There is, yes, Yogesh, you can ask question.
Yes, sir.
Yogesh?
Uh, yes, sir. Am I audible?
Yes, yes, you're audible. Please.
Sir, you mentioned confined machinery with the joint reinforcement. So I want to ask, is this the conventional reinforcement or it is a strip? It is in strip form.
No, actually are rebars. I mean, very small ones.
Okay.
I mean, they have a diameter maximum of 1/4 of an inch. And but because they are very small, they are high strength steel. They have like 600 megapascal, 600 megapascal shear yielding stress. So although are very small, they can develop large forces, but are very small. This actually we call them wires because of they are very small. And in Mexico, it's customary that bars less than a quarter of an inch of diameter are called wires. And so we actually put wires in the joints. The wires, I mean, these small bars, they have a very special characteristic. There is no way for the bar to be lapped. It had to be one piece, and it should be anchored in the tie columns. This is very important because
Please,
so
please, please mute your mic. Yeah, please mute your mic.
no, sorry, I can't hear. The sound is very very poor.
Yeah.
Okay, sir. Yeah.
No, sorry, I can't hear.
Yeah.
So are not strips, okay? The question was if there was kind of strips or what kind of reinforcements was are bars, okay?
Okay. And is this the single wire or like strand type? It is wounded wires.
Uh, I couldn't hear well. Eh, Let me say something. For example, in other countries, they use this joint reinforcement that have some shapes. For example, like a truss-like um, shape. They use it in the United States. They use this truss-like reinforcement in the joints. We don't use that kind of reinforcement in Mexico because this truss-like reinforcement need to be welded. I mean, at some points, and this welding we have found in the past in Mexico that are very brittle, and they tend to break. And this breaking of these weldings produce abrupt changes in the strength of the walls, and make them fail kind of abruptly in sometimes. And so we decided that this type of ladder-like or truss-like reinforcement should not be used, and we preferred straight bars that should be well anchored in the tie columns.
Okay, sir. Thank you, sir.
Okay.
Sir, one question that we are facing the problem of corrosion in RCC. At the same type of problem we are facing in confined masonry also, or
No, and you're right to ask because we don't have corrosion problems in Mexico City, but in other parts of the country we do have. And so there are provisions that there is enough mortar to cover the bar, so to prevent the corrosion. So yes, should be well covered, and there is an eventual problem with blocks, for example, masonry blocks that have large cells or openings in the units, because the reinforcement is sometimes is located not not in the shells of the units, but in the middle of the block. It can be that way, but it is clear that if the structure is in a place that have corrosion problems, that is not a good solution. And so because then you will have parts of the wires that are not well covered with the mortar, and so they will be corroded. And in the code in Mexico, because we don't have that kind of problem, you can put the wires even in blocks, and parts of the bars are not covered with mortar, and are okay, no problem. But in the coast or other parts of the country, that won't be a good solution. So you need to, in those cases, be very careful to provide enough cover of the bar, and there are some specification for that in the code to provide enough cover of for the bars to be protected from corrosion.
Thank you, sir. Now I think there are no more questions. So we have. Yes,
if
sir.
someone if I didn't answer well the questions, or if anyone wants to I mean put forward some other questions, I would, if you can collect them, I can gladly answer them by writing, if that is possible. I will
Sure,
be
sir.
very pleased to answer your questions.
Yeah, sure, sir. Thank you, sir, for that. Sir, we have Dr. Svetlana Breze with us. She gave your reference, and I think therefore we are able to invite you. Svetlana ma'am, your comment, please.
Is both Juan Jose and I are sorry that we are not in India. That would be much better. And the second is thank you so much. We really enjoyed both our time spent in, and we were together actually in several occasions. Thank you very much for excellent lecture. And this is going to be a very good introduction for tomorrow's lecture, because we will be talking about design of confined masonry walls according to the new Indian standard, which is just about to be issued. And it actually, the Shear this study that Professor Juan Jose mentioned is the same as is adopted in Indian code. So it is a very good background for what Indian code contains for the Shear design, at least, and other topics were also very, very interesting. And I believe such studies are currently not done in India, and it's very important. And confined masonry technology is new, so it's very, very valuable for Indian students and professors to see the studies that have been done in Mexico, which is at the forefront of this research. So thank you, Juan Jose, very much for the lecture.
Thank you, Svetlana. Okay.
Thank you, sir. And sir, we want to take one photograph with you online. So I ask all the participants to switch on your cameras. So we have one photograph with the sir.
Excellent.
All the participants, please switch on your camera. We want to take one photograph. Basically, if it is offline, then definitely we'll have a very good photograph. But in online mode, also you want to keep your memory, sir. All the participants, please switch on your camera.
And sir, please stop sharing your screen so that we can see full screen.
I need to stop my sharing, yeah?
Yes, sir.
Yes, sir.
let me. I already stopped my sharing, isn't it?
Okay. Just a minute.
Okay, they are starting to show.
Ashwin, if it's done, please tell.
Yes, just a minute.
Yes.
Okay, sir.
Okay. Yeah. Over.
Thank you.
Thank you. Thank you. Over to
Ready?
Ruvi. Yes, Ruvi, please.
Yes, sir. So thank you so much, Professor, for your lecture. We've loved it, and we'd really like to have more of your lectures soon.
Thank you.
If we
Thank
can.
you very much.
Yes, sir. So now I'd like all the participants to just wait for like 15 minutes. Ma'am, Svetlana ma'am will take a 15-minute break, or do you want to continue?
Okay, then I say goodbye and thank you again for the invitation. I was very
Yes, sir.
happy to
Thank you,
to.
sir.
It is too late in the
Okay,
Mexico,
then.
right?
Yes,
Yeah,
sir.
thank you. Thank you,
It's
sir.
almost
Thank you.
2. Thank you so much, sir.
Okay, bye bye then.
Thank
Bye.
you.
Bye.
Bye.
Bye, Svetlana.